All right, Matt, would you introduce yourself, please?
My name is Matt Minton. I'm with the McComb Group. I'm the steam product manager for McComb Group, and we're at Cloud Mechanical today.
RSES.
RSES, that's correct.
Thank you.
Thank you. Appreciate it.
Floor is yours, sir.
Thank you. So I'd just like to kind of start out, and we we agreed that we'd talk about steam traps today, but I'd just kind of like to start out and say, ask what's the level of steam knowledge here? You guys obviously you've got a lot of experience. Do you guys do a lot with steam?
Rick's been involved with it a lot.
He says zero. Yeah, he's always the guy that says nothing that has done the most. So you guys do a fair bit of steam, high pressure, industrial steam, commercial stuff?
Most of it's low.
Okay. Any superheat left up here at all?
There is, but we're not involved in it.
So probably Cleveland Thermal and some places, a little bit in some processes, maybe in a paper plant. There's hardly any of those left.
We're not doing much process steam here. We've got a couple of plants.
Okay. Well, goal today is just keep things super informal and just talk in the most basic form that we can. I prepared some slides today, threw it together kind of last minute. What I thought maybe be good to talk about, and if we want to talk about something else, just steer it. Please let's have questions and answers back and forth. Something I say it doesn't make sense, call me out on it. But otherwise, we'll get into it. I did want to cover just a couple of fundamentals, and we don't have to spend a lot of time on it, but want to make sure that we kind of all have a comfortability factor with just the most basic, some of the fundamentals. So getting into it, appreciate Doug and Tom setting this up today. Thank you guys and especially thank you for ordering the food. I don't get to do a lot of steam jobs with boilers that big, but occasionally it comes up.
I Photoshop that one.
It looks like it.
Bullshit on that. Okay, it's being real.
It looks like it. Believe it or not, I was in Michigan getting a training on a Friday, and I had to drive right by my house and go about another 2 hours to go to that. I got there about 7 o'clock on a Friday night to help them, not with the boiler. They were just doing service. So I helped them with steam. I was helping them do some steam stuff, but I'm like, it's not every day you get that photo op. So anyways, couple fundamentals, steam temperature is the temperature given at a given pressure, which begins to boil at 0 to 12, right? We know that water can exist in 3 states. There's, Kentucky, Indiana, Illinois, Ohio. 3 states is obviously, a solid, below 32, water up to 212, and then it becomes steam. It's all relative to sea level. Every 1,000 feet you go up, we're going to produce steam at one degree lower. So not anything major there. Sensible heat, the energy contained in liquid water at a given pressure. Sensible heat is obviously what we can sense. Like you throw a pan of water on the stove, you turn that stove all the way up, you got boiling water. It's what you can sense with the thermometer. Generally, sensible heat. We're going to get to 212. We're not going to go over that until we want to stick a lid on that. Try to develop some pressure. But generally, sensible heat is what we can sense with a thermometer. We could get way more in depth, but there's really no point. Latent heat, that's the good stuff. That's what we're actually after. It's what we're going to use in our process. It's what we're going to use in our heat exchangers. It's what we're going to use in our kettles. That's the stuff that we're actually going to use to heat things up, and really what we're trying to get out of this heat. BTU, or British Thermal Unit, is simply defined as the amount of heat required to raise 1 pound of water 1 degree F. All your equipment that you're looking at in the field that shows BTUs, I think you guys all know, you just drop the last 3 digits and it roughly gives you pounds per hour. The correct way to do it is divide the latent heat by the pressure, but very close. If you're in the field, if it says 1,000,000 BTUs, you can safely guess that it's 1,000 pounds per hour. Unlike electronics, where I used to have to take mean time between failures 9 places to the right of the decimal, steam ain't like that, as we all know. It's pretty close is good enough. Steam and condensate flow, both are measured in terms of 1 pounds, 1 liquid to 1 vapor. It is a 1-to-1 relationship. We take 16 ounces of water, we throw it in the boiler. That blows up to be 27 cubic feet, 1 pound of steam. In a perfect world in steam, if there were no leaks, that would, after it gives up its latent heat, turn right back into that 16 ounces of water again, and we would hopefully return that right back to the DA or the feed water and reuse it all over. How's it going, man?
Right.
Flash steam is the steam that's formed when condensate is released to a low pressure, revaporization. Steam, when it hits lower pressure, it has no choice but to flash. Guys like me have been accused of being stack chasers. We drive by plants and we see, you see that little bit of steam coming out, kind of looks like, doesn't really have a whole lot of velocity. That's generally flash steam. It's when we see those plants that have the first, half inch of it be clear with a lot of velocity, we know that plant's blowing a lot of live steam through, and there's an opportunity for me. They're wasting a lot of steam. Flash sometimes accidentally gets, traps. There'll be a little bit of flash around a trap, and people might think a trap is blowing by, but in many cases it's not. It's just actually flash. Back pressure, not talking about my back today, even though I'm feeling some back there. Back pressure is just, the existing pressure in a return line. If we're going up 20 feet, it's real safe in the field to assume that's 10 PSI of back pressure. It's actually every 28 inches is 1 PSI, but when we're trying to determine and walking a plant off, all right, we got a 10-foot lift there, we've got a 20-foot over here, and many times, because nobody has pressure gauges anymore, and when they do, usually they're broke. So, we got to kind of figure things out. It's frequently in the field. Differential pressure, delta P, is just simply the pressure difference between the inlet pressure and the outlet pressure. Steam traps aren't pumps. They work off of differential pressure. You got to have higher pressure on the inlet than the outlet. Differential pressure is actually what makes everything move. Without differential pressure, we got condensate pumps, but without differential pressure, nothing would happen. Saturated steam is a dry steam. What do you guys think of when you hear the term saturated? A lot of people would say wet. You say saturated, I think wet. It's really the opposite. Saturated steam should be dry steam. Should be 100% dry. Very, very seldomly ever is. Steam that contains no free moisture. Superheated steam, on the other hand, the amount of additional heat added to steam beyond its saturated state. So, for example, Ohio State, in my backyard, their spec is 185 PSI at 585. So people, there's not a lot of superheat, so a lot of people don't understand it, and we're not adding any additional pressure, we're adding additional temperature. And in the case of Ohio State, roughly 42 miles of underground steam piping, and if you want to get steam, in a district heat fashion to West Campus, and you want it to be steam when it gets there, then you're going to superheat it. And then we'll use de-superheaters, which basically look like a spool piece in line, and they got some atomizing nozzles, which all they really do is inject condensate right back into that superheat, and then bring it back down to the saturated steam level. Wet steam is steam carrying droplets of water suspended in steam space. We're going to talk more about this. Even though we're here to talk about traps, I think all this stuff is applicable. You guys know all this, and it's like, hey, this is old news. We don't want to talk about it. We can get past it, but I think it's important to cover it if there's one person in the room that's not familiar with it. Wet steam, again, it affects the dryness fraction, okay? It carries no latent heat, and it definitely affects the quality of steam. When we talk about quality of steam, if we say you've got 90% quality of steam, we're talking about 90 parts steam, 10 parts water. It's that simple. You got 80%. What is it? Nobody really knows. I can tell you that there's manufacturers that have come out with steam quality meters in the last several years. They work pretty well, but we'll talk about some other things in regards to knowing that. So back to the sensible heat. You know, this is sensible heat. It's what we can sense with a thermometer. You're not going to get over 212 unless you put a lid on that thing and give it some pressure. British thermal unit, 1 BTU of heat energy will raise 1 pound of water by 1 degree F. 1,000 BTUs will raise 1,000 pounds of water by 1 degree. You can see that. Just some quick fun facts there. 3 states water can exist. We talked about that already. So there's one thing I want you guys to get out of this slide. Really. So we've got gauge pressure over here. We've got temperature. We got sensible heat. How's this? Yeah, there we go. So we got sensible heat, we got latent heat, and then we got volume. So the whole purpose of why we are producing 100 psi at the boiler, yet usually our shell and tubes or plate and frames in many cases are 15 psi, lower pressure, is because steam is a compressible. If we want to generate 15 psi at the boiler because our shell and tubes are running off 15, we could do that. But what would happen? Our 6-inch steam main might become a 16-inch steam main. Our 6-inch strainers might become 16-inch strainers. On and on and on with all the associated equipment. So steam is a compressible. That's the big news. We generate at high pressures. So there's really 4 parts to a steam system. Generation, that's the boilers and steam generators. There's the distribution, that's the piping systems, which we want those to be as small as they can be. We don't want to buy 16-inch pipe if we don't have to. We're going to utilize it, and that's where we're going to utilize it. Our heat exchangers, jacketed kettles, all the different areas, autoclaves, depending on what kind of a place we're generating steam for. And then we're going to return it. After it gives up its latent heat, goes back in the condensate. We want to send that back to the DA. We want to send it back to the feed water and reuse that. But again, the importance of this slide is relative to volume and latent heat. You notice here, we've got right at 0 gauge pressure and 212, there's 100 degrees sensible heat. There's no latent heat yet, and there's really no volume. But as soon as it takes that phase conversion and blows up 1,600 times and becomes a pound of steam, we've still got the 180 in sensible, but look how much latent heat there is. It's 970 BTUs of latent heat. That's a lot. Look what happened to the volume. 26.8, 27 cubic feet. It's like a old walk-in phone booth for those of us that are old enough to remember those. When we get up to the 100 psi, look what happened. You got more heat, 309 sensible, but your latent heat went down. So the interesting thing about latent heat and compressing steam is the higher the pressure, the less latent heat. And you know, there's the big news, right? We went from 27 cubic feet to 4 feet. So that's what we're trying to talk about here. Steam is a compressible gas. Everybody knows that the saturated steam has a corresponding temperature for pressure, right? Very standard stuff, but I just put it up there to point that out. And you know, 100 psi, 338 degrees. There's your 4 cubic feet. Then, you know, there's your 309 sensible, 880 latent, and then total heat is 1,189 BTUs. Does that all make sense? Saturated versus superheat. Again, the quality varies with the amount of water vapor present. Adding heat improves the quality. Pressure and temperature are related by the saturated steam curve. when you take superheat and when you take saturated steam, like at Ohio State as an example, you create saturated steam, you run it across the turbine, you elevate it, create the superheat. That is free of all moisture. Actually, those turbines don't like even a drop of water, right? So the big difference here really between saturated and superheat is that superheat is 100% dry, and that we're just elevating the temperature, not any given pressure, and there's no longer a corresponding pressure and temperature curve.
What are they using for superheaters?
It's OSU, I think it's GE.
Is it economizer style, or are they got separate burners on?
No, they're yeah. And look, they're in an effort of de-steaming over there. Like many of the people are going to, but we're not going to lose the steam when we're talking process, when we're talking the pharmaceuticals and all the different areas, the food plants. So superheated steam, it's a very dry gas, realized by adding additional heat above the saturation point. As we said, the pressure and temperature are no longer related. And so this is that example, 185 psi at 580 degrees F. So there's basically an additional 382 degrees of superheat for that. And again, why are we doing it? It's so that we can get steam all the way to, who knows how many miles away to that end use. I just give you a picture of the wisp room because there's all the old great stories about walking in the steam tunnels. Superheated steam really barely has any moisture in it at all, like none. And so when there's a leak, how they look for the leaks is they walk around with the old whisk brooms or a piece of cardboard, and they wait for it to see the whisk broom get knocked apart or the cardboard get knocked apart, and they know to stop. Yeah, exactly. And there's an old story about a guy in Cincinnati, which I think is true. I've heard it from a good source who was in the field back at that time. A guy that put his hand really close to a leaking flange of superheat, and it cut his finger off and cauterized it. It never bled. I mean, it was that fast. Cut his finger, cauterized it, done deal. So pressure measurement, you guys are refrigeration here. I think you understand, all the nuances of vacuum and pressure and 14.7 atmospheric, which is holding us down to the ground. Again, back to this. You guys don't need this, but safety. We love it when things are labeled. So I'll get us into the traps here.
Label correctly.
Well, label correctly. Yeah, I mean, high pressure, 600-pound steam. It's nice to know. As my mentor tells a story about being on boilers at AEP, he's on top of a boiler looking at control valves, and he says, all right, what's your pressure? And he writes it down, and the guy says, medium pressure. And we need better information than medium pressure, but we're in the field, and he writes down medium pressure, and he's like, well, what is medium pressure? 2,500 psi. Okay. Yeah. So steam, it's hot. It's real hot. Again, we talked about it really quick. Steam generation. That's our boilers and steam generators. Distribution, high, medium, and low pressures. Steam utilization. So the high, medium, and low pressures, it's all ambiguous terms, really, other than the fact that code dictates low pressure is 15 psi and below. And then everything above that technically is, some people call medium pressure steam 50 psi, and some call 2,500 psi medium pressure. Condensate recovery, it's either coming back via gravity or pumps. This is just a kind of a random picture of 4 parts of the steam system. Again, we're generating it here. Notice that we've got our takeoffs off the top of the pipe, not off the bottom of the pipe. We see it enough where it comes off the bottom that it's why the slide is still in here. We want those takeoffs to come off the top. Notice that every device, has a trap. We like to see that. And then, I don't need to tell you guys, but I'll just say it anyways, that on the steam mains, about a ½ inch every 10 feet of pitch. Some people have slightly different measurements on that. Get it going the right direction. ½ inch every 10 feet sufficient. Is that, Tom, about what you agree with?
5% will do it.
There you go. Yeah, even said better, 5%. And then obviously on the condensate, so pitched away from the boiler. On the condensate return, we want it pitched back to the feed water, the DA. Same measurement though, about 5%. There you go. We bring up concentric versus eccentric. We're not going to get deep into water hammer today and a bunch of different things, but anywhere that we've got a spot where we create low spots is a opportunity for water hammer, and it will happen. So, in the case of if we're reducing either a control valve station or a PRV station, because those valves are never line sized, we want to use an eccentric reducer where it's not going to create this pocket. And, same thing, sagging mains, never good. Steam takeoff of the top, sizing steam mains. So not going to spend a lot of time on it, but as far as the velocities go, if things are sized right, generally in the industrial plants, we're about 120 feet per second. If we're in an operating room, maybe over a library, next to a library, we're going to size that pipe for a much lower velocity. But what I see happen pretty frequently is in industrial plants, the pipe's already undersized. So it's going to be in excess of that. And, that's where stuff gets torn apart, fittings get torn apart. Pipe gets sized, despite how easy it is, it gets sized incorrectly pretty frequently. Again, just a quick note on the concentric, anywhere that there's a low spot, and we give a slide on the strainers as well. So condensate is not wastewater. It's actually pre-treated softened boiler feed water. It's the water's expensive, the gas is expensive, the chemicals are expensive. We want to return as much of that back to get used as possible. We've got to keep these plants efficient. So you can gravity feed condensate back, or you can pump it. Those are the two options, really.
Can you go back a slide?
Yes, sir. So we got traps on, notice we got traps on, pretty much every kettle there. Got some shell and tubes there. Every, in the case of steam coils, you guys probably deal with some steam coils. Recently at a chemical plant that I've called on for a lot of years, they've got 2 separate coils and they're trying to drain those with one trap. Doesn't work out very well. One of those coils is going to win. And what does the loss look like? Well, this time of year, it's frozen coils, at which to the tune of, for them, I think it's about $40,000 a coil. So we're in the process of redesigning the system so that because they've done it years and years and years in a row, and they just keep throwing coils at it. And the conditions have to be just right, but
It only takes a few minutes.
we don't double trap things. In other words, they call it gang trapping. We don't do that. I've got a piece of equipment and put 2 traps. We don't do that. And then we don't have 2 pieces of process equipment with 1 trap. You can take a lot of process equipment, drain it into a standard, like a flash tank or whatever, and you can trap that. But if you try to drain 2 coils using 1 trap, one of those coils is going to win. And when the conditions are just right, one of them is going to freeze and pop if it's taking in cold makeup air. So nothing too big to talk about here. I just wanted to go through some of this stuff really quick. Again, we're going to get into the weeds here on traps a little bit, but we're generating steam. You know, when we talk about drip traps, it's a real simple deal. Like, it's a 1/2 and 3/4 inch trap 99% of the time. People always say, well, what's the right trap? Well, it's like, there's multiple answers to that. It's kind of like the way I was taught, you a Ford guy or you a Chevy guy? What do you like? Now, if we're talking low pressure steam below 30 psi, that TD trap there wouldn't be a good choice. And we'll talk about more of that. If it's, you could use a bucket there if it was below 30 psi. These TD traps, regardless of the manufacturer, they're rated all the way down to 3 psi. They do not work very well at all, especially under 20 psi. You get down into 10 or 15, and they just don't work. So my first choice on a drip trap for a steam main, if we're above 30 psi, would be a thermodynamic trap, and we'll get into more of the weeds on that. But it's got a disc in it, and we've got an animation on that, and we'll talk about that. But that'd be my first choice. Tom might have. What's your first choice for a steam mains drip above 30 psi? You a bucket trap guy or
Above 30?
Yeah. Yep, inverted bucket. Inverted buckets do great when people have dirty steam. We'll see that the head and seat is in the top of that, so dirt falls. So there's advantages and disadvantages of each type of trap, and we're gonna get into those. But you notice right here on the process steam, in my opinion and most people's opinion that are worth their salt at all in steam, it's going to be an F&T trap. It's going to be a float and thermostatic trap. Now, we see a lot of buckets used in process, and if you got a steady, non-modulating load, okay. They do a really piss-poor job of venting air, and air is a big deal, especially on startup, or if it's not a steady, consistent process. So always, I'll just leave it at, I say process steam traps are just floating thermostatics.
I never thought of this before. Is there a fluid volume rating on traps?
Yeah. Well, I mean, it's capacity.
Like a bucket or an FT?
Yeah. I mean, it's generally, we're sizing them based on pounds per hour. But yeah, I mean, we can convert GPM to pounds per hour and pounds per hour to GPM. We always, again, sizing, and we'll talk about it more in here, but sizing a drip trap is real simple. And as I was taught by my mentor, when you get a phone call for a steam trap, you're kind of like at a fork in the road. You need a drip trap, or you need a process trap. If it's a drip trap, it's a real quick and generally easy discussion and conversation. Now, what you'll hear a lot is guys will say, "Oh, I don't know. I don't know if it's a drip trap or a process." And that's where you got to talk to them. Hey, where's the trap at? Let's start at the boiler. Where is are we draining just off of a steam main, or are we draining like a shell and tube or a plate and frame or a jacketed kettle? So sometimes you got to talk people through that, but you're really at a fork in the road when you get that phone call on, hey, I need a steam trap. And if it's a drip trap, it's a pretty easy conversation. If it's a process trap, we're going to need some information. Now, if you're replacing, hey man, I'm just replacing one of these and I'm reading you the stuff off the tag. And the question we like to ask is, has that trap always worked well for you? How long did that trap last? If it lasted a year, well, maybe time out. Let's talk a little bit. If you said that trap lasts 10 or more years and it's always, hey, we've never really had any problems. I got no problem you quoting exactly what you got in there. And we're not here to make anybody's life more complicated. You guys are all in a hurry, right? And to get quick information, but we always want to make sure that y'all get the best thing. But we're not here to try to stand in the way and make things more complicated than they need to be. What do you think when you hear the term saturated? We talk about it. A lot of people say wet. And saturated steam really should be dry. We talk about the dryness fraction again. 95% quality refers to 95 parts dry steam, 5 parts condensate. You know, everybody thinks that the condensate is just flowing at the bottom of the pipe. But there's actually, in wet steam, there's a lot of entrained moisture that's right in the flow of the steam when you don't have good quality steam. And that's really super problematic, or at least can be very problematic. If we're using saturated steam with no superheat, how can we ensure that the steam is of good quality? And it's very simple. It's a moisture separator. It's not a sales pitch. These things work wonderfully. They're dumb hunks of cast iron. This is basic. So if you've got a 4-inch piece of pipe, the inlet right here on that separator will be a little larger. And the whole point is to kind of slow the velocity down right here, which helps that whole, these little water droplets are the entrained moisture we're talking about. We're trying to get those moisture droplets to separate from the flow of steam. And that's why, again, if the 4-inch pipe is this big, the inlet on that separator is going to be bigger. And then from here, it's just a very simple, these little hooks here, and we're just forcing the condensate down. And then we just, you know, in the case of a moisture separator, this is just an F&T trap. And these work wonderfully on compressed air. That's the other thing people miss, that everybody's got wet air. And these babies work, and you know, airlines are small, 1/2 inch, 3/4 inch, 1 inch. The separators are very inexpensive at that point. When you get into the 3 and 4 inch and 6 inch, sold a 24-inch separator before, those get very expensive. But we could talk for hours about that. We're not going to. But these are wonderful and certainly worth their weight. There's no maintenance really associated with these guys at all, other than, you know, this type of stuff. You see separators up here? Not very often. Dryness fraction. So we talked about that. This is just kind of proving it out. The saturated steam at 100 psig is 338 degrees F. If you got 100% quality, you got 881 BTUs of latent heat. If you got 50%, maybe you're trying to produce more steam than your boiler will allow, and you're getting carryover. That's where you're going to get that kind of low quality steam, 50%. And that's where now, instead of when your process says you need 900 or 800 BTUs of steam, you're producing half of that. So just something to think about. Where we put these things is in front of, right coming off the boiler, in the header, especially when we may have a carryover situation. We put them in the distribution system. We put them upstream of all PRV stations. So when you guys install a PRV station and you put a 100 mesh strainer in front of it and then a separator, because, you know, again, my mentor, the way he trained me is he's like, have you ever, anybody in here ride a motorcycle? You? So, nice day, going down the highway, it starts to rain. What's the water feel like when it's hitting your skin? Feels like BBs. What do you think it's doing to the inside of the valves? The thing that's tearing all the valves up and tearing all the equipment up is the moisture. So it's, you know, doesn't matter whether it's Spirax-Sarco or Watson McDaniel or Armstrong. Pick a manufacturer, they'll actually double their warranty on the control valves and PRVs if you put a 100 mesh strainer and a separator in front of it, moisture separator. So, and we don't, you know, look, good piping practice on the steam trap says that you're going to stick a strainer before the trap and a check valve after the trap. That's a 20 to 40 mesh strainer. I don't care how you install that. But when you're installing a 4-inch flanged strainer in front of a PRV, you don't have it hanging down. You put it on its side, because otherwise it's like a 5-gallon bucket of water, and all that happens is it gets picked up and flung and hits that control valve, and that's what kills everything quickly. So again, we got a separator, we got a strainer, it's on its side, and we've got a little F&T trap here. We've got a little F&T trap off of this. We've got a little TD trap off of this filter, clean steam filter. That's just that's a good looking clean steam hookup right there. And if any of you guys are familiar with this book, this is they used to hand these out very frequently. This red hookup book from Spyrex is very good. Most of the other manufacturers that I know, they carry these in their car because it's a great resource. You can get these for free from Spyrex online. Again, it's not a sales pitch. I'll leave you guys one, and there's another book, but there's no, this isn't a catalog. This is all about hookups. This is all about specific gravity. This is what I consider to be the Bible of hookups.
What's the loss detector?
So the loss detector is if the steam trap is blowing through. And that's the old, in this case, this is kind of like a Spyrex Sarco hookup, really from that hookup book. And really what it's doing is just detecting if any steam is blowing through. And then it would give you an alert. And of course, we've come really far in that technology now where these no longer are a wired thing hooked into a control panel. They're actually wireless. We use heart gateways, and they're wireless. And so these things channel hop. They'll go so many feet, and some wireless gateways you can get 100 devices. Some you can get more. Some you can get less. But where it really makes sense is like on say if you're a food plant or you're Abbott Labs, and you've got a critical batch process. And hey, if anything gets screwed up and we're just slightly off in our temperature, we want to know like right now if we've got a steam trap blowing through. And you're going to get an alert to your phone. It's going to go off in the control room. So that's the old way of doing it, and we've come really far. Technology in many ways isn't great, and in some ways it is. Typical PRV, again, we got our moisture separator, we got our strainer on our side, we got gauges with pigtails, we got this downstream sensing line that is angled down. If it were angled the other way, we'd have condensate on our pilot. And the news here is that these PRVs are not line sized. The outlet, what did we say about steam? It's a compressible. You're reducing pressure, the volume goes up, and you can only fit so much steam through a given pipe size. So if we were to just line size, if that's a 1-inch PRV, and we had 1 inch on the inlet and 1 inch on the outlet, we would be choking the steam down, if that makes sense. So again, same, we could use a TD trap here. We could use, the nice thing about the float and thermostatic traps, which we're going to get into here real quick, is that they will basically handle the condensate as rapidly as it's formed. So we've seen this already. This is the eccentric reducers versus the concentric, and in front of PRVs, we don't want to give opportunities for that delay. It's just going to get picked up and thrown at the valve and kill that head and seat a lot sooner than it really should. These are the moisture separators that you're going to find right off the boiler. These are more the kind that you're going to see in the pipeline. These are the little guys, 1/2 inch, 3/4. These might go up to 1. That's what you'd use on a small steam line or like compressed air. These work great on compressed air. So if cold flowing water does this to granite, what's your condensate doing? to your equipment, right? Moisture separator sizing, there's actually a half-page formula you can bang out. It is always line sized. 100% of the time, if you've got a 6-inch line, you're using a 6-inch separator. If you've got a 1-inch line, you're going to use a 1-inch separator all day long. Many people ask, what is the pressure drop on that? What's the pressure drop? Everybody's concerned about pressure drop. What's the pressure drop on that separator? It's what they call an equivalent length of pipe. So if you've got a separator that's 24 inches long, the drop is going to be the equivalent of a 24-inch piece of pipe. So it's really negligible. This is what we talked about with the strainer. Again, on a 20 to 40 mesh strainer before a steam trap, which is, again, good piping practice dictates every steam trap has a strainer right before it, has a check valve right after it, so you don't backfeed steam in. We can talk about, okay, is that a horizontal line or vertical line? We can get in the weeds and talk about that. But really, this here is meant to show you in front of a PRV or a control valve, if you've got that strainer hooked up that way, what you're going to do is create a big pocket of water that's basically just going to get picked up and thrown right downstream. So we just ask you to put those on their side. And again, that's the representation of that. And, again, in front of a control valve, this, you see this 3/8 tubing here, and there's 3/8 copper tubing here, and you go, oh, gee, it doesn't. There's actually a lot of really fine orifices in these things, and they get clogged up pretty easy. So that's why you really want to use a 100 mesh strainer. And if you go to a place and they're having problems with PRVs and they don't strain at all, you can bet that it's got something to do with that. That may not be the whole problem, but that's it. And then, it makes a lot of sense to blow that thing down. If you're going to put it in, you better blow it down. And then we all know we don't use oil-filled gauges on steam. Those are really for pumps, and we want a dry gauge. And when we talk about gauges, you go in and look at a 30 psi steam application, somebody's using a 0 to 300 gauge. Gauges, you look at most of them on the back, it'll say like 212. It means 2%, 1%, 2%. So in the middle third of that gauge, it's 1% accurate. It's most accurate. So if you've got a 50 psi application, you're going to spec in a 0 to 100 gauge. You're going to be right in that middle third. All right. Pigtails and ring siphons. I always call them pigtails. So getting to steam traps. Why do we need them? What's the point? Air venting, condensate removal, thermal efficiency, reliability. All right, well, what's that mean? So a basic definition of a steam trap, you think about it like if you take an F&T trap and you draw a line right down the middle of it. Its job really, if you kind of reverse the word steam trap, it's trapping steam. A lot of this equipment, if you just kind of reverse the words, is by definition, an automatic valve designed to stop the flow of steam so that the energy can be transferred. So it's basically holding steam back until it gives its latent heat up, it turns to condensate and goes on down the line. That is the job of a steam trap. It also discharges condensate within its size range and air, including non-condensable gases. Air is the big one, especially on startup. If you want to use buckets on process, and I don't care whether it was that perfect, steady, consistent load that doesn't modulate at all, on startup, you're going to have problems. It's going to take a lot longer to get started up, and you're going to have to crack strainers, the valves on strainers or something to get that air and the non-condensable gases out. Air is, you guys know it likely a lot better than I do, air is a massive insulator. Massive insulator. We're trying to heat stuff up, not insulate it from the heat. So steam trap purpose, again, it's to hold back live steam so that the steam can give up its latent heat to the process. We talked about that already. Latent heat, I think, translates, roughly to like invisible. Live steam is invisible. Discharge condensate. so that more steam can enter the process, because condensate will only give up its heat when it changes temperature. It flashes. Again, I got this, in big and bold, remove air. We're trying to get air out. And, the trap that handles air the best is a floating thermostatic. It's got, and we're going to look at the animation here, it's got a thermostatic air vent in it, and it by far handles air the most, and that's why it is a process trap. These traps, thermodynamic, TD trap, they don't do very well with air. These are the ones that I said, below 30 psi, they don't work very well at all. You start getting below 20, you get into 15 and 10. I've seen them used, and people say, yeah, they're fine. Like, hey, you have any problems with that? No, it's fine. Well, they don't work very well. Yeah, they don't work very well. You sit on a rusty nail long enough, you get used to that too. So it's an automatic valve that stops the flow of steam and holds it back. Steam traps are not pumps. People have that common misconception that it's a pump. It most certainly is not a pump. It holds back the steam until it gives its latent heat up, converts, and does the phase change to condensate, and it passes. So the job of this trap is to close in the presence of steam and hold it back. It opens in the presence of condensate, removes air and non-condensables, uses the heat energy so that it can be transferred, and does not pass live steam. Let's talk about traps. So the typical locations for condensate: drip legs and drip pockets, that's steam mains. Generally, the steam feeding a process. That's where, like, somebody calls, hey, I need a steam trap. You're at a fork in the road. We talking a drip trap or a process trap? This is, some people call them dirt legs, drip legs. There's all kinds of, what do you guys call them in the Navy? It's just call them dirt legs. Drips, yeah. Heard them called a lot of different things. Another spot for traps is going to be on tracer lines. You might be keeping something outside warm so it doesn't freeze in the winter, but you also, a lot of tracing, and I don't know if you guys have a lot of tracing up here or not, but you use a lot of tracing to, say, in a chocolate factory. You're going to want to keep that chocolate heated up. You don't want to get it, to the point where it won't move in the piping. So we'll trace lines. And those are very basic, TD traps work really well for that. There's, if it's outside, you really don't want to use any traps that are going to have a water level. It's one of the reasons we really like the TD traps in an outside cold application, because a bucket's going to have a water level, and a floating thermostatic's going to have a water level, and it's just going to freeze and crack. So TD traps are a really good choice for that. And then, other spot, the most important, is on the process. So that's the steam that we're using to heat the products: jacketed kettles, shell and tubes, plate and frames, air handlers, that type of thing. The condensate is certainly too valuable to discard or just run to drain. So a few different types of traps fall under a couple of different categories, I should say. The TD traps that we talked about, they're really kinetic traps. They're running off of kinetic energy, and call them a TD trap, thermodynamic trap. They subcool. So what is the subcooling? That's where actually that steam has to subcool 2 to 10 degrees before anything really happens, before it passes it. It's not like an F&T trap where it's just going to pass the condensate. You see that 2 to 10, like the floating thermostatic, there's no subcooling whatsoever. What's happening here when you're subcooling is condensate is backing up in your system. Sometimes that's not a big deal, and sometimes that is. As far as air venting, that's a very important column there. The TD trap is not very good for air venting. So to me, this trap has one application: drips 30 psi and above. It's my first choice. All the way to 600 psi. A lot of places you can go into an end user that's got Watson McDaniel and Spyrex and Armstrong and all kinds of bastardized different traps, not that there's anything wrong with any of those manufacturers. They all make good equipment. But storerooms, you got to think about the storeroom for a minute. I could standardize all drips on one trap, and they're 1/2 and 3/4 inch. So instead of having 20 different SKUs in your storeroom, you can have 1 or 2. Density, that's your float and thermostatic and your inverted bucket. Again, on the subcooling, there's none for an F&T, and the air venting is absolutely excellent. It's the best one by far. An inverted bucket, you get 0 to 8 degrees of subcooling. Again, inverted buckets are great for steady loads. Modulating loads are not good, regardless whether it's process or distribution, because buckets will lose prime. And, we're going to get into a little bit more of that. They have very limited air venting. And again, if you've got a steady pressure application, they do well. If it's modulating and there's air, and if it's a system that gets shut down on the weekends and started up every Monday, it's going to take forever to get those heated up, and you're going to have to open valves and kind of do what we call a supervised startup. Thermostatic traps, these I really see more as like an air vent. We use them a lot, and we started doing some more pharmaceutical jobs down in Columbus. There's kind of a boomtown thing happening, and we've got some pharmaceutical and food plants and different things. But you'll see these a little bit in hospitals on certain applications, but we really don't see a ton of them, and I see these really more as like an air vent. And look at that. Look at the subcooling, and even worse, the bimetallic. So the bimetallic's just 2 dissimilar metals, and as it heats up, they separate, and that's what seals off the head and seat of the trap. And look at that. I mean, that's an air vent. That's not anything I've ever even sold. I'm sure they have their applications and their spots, but I certainly don't. Liquid expansion traps, we could talk about them for a while, but it's really, if you're doing air coils, these are basically, there's a freeze-ton. One brand calls them a freeze-ton and a thermoton, and basically one senses the temperature of condensate, one senses the temperature of outside air. And why is that important on those coils at that application of the chemical plant that we talked about? We put some liquid drain. It's really a steam trap, but once the condensate gets to about 34 degrees, it dumps. So we're not going to freeze those coils. I mean, if the worst case scenario hits, we're not going to freeze those coils. That's a liquid expansion. Also can use these on like eye wash stations outside, for the winter, so that the lines don't freeze and break. Categories of steam traps we talked about a little bit. We'll talk more. So again, we got the TD trap. It's velocity driven, and this little guy will make a lot more sense when we watch the animation of it. But again, my first choice, 30 PSI and above, and all the way to 600 PSI. So a ball float is basically an F&T, is another way of saying it. That's more like a high capacity version. It's a mechanical density driven. So it's basically inside, and we'll see it on the animation. It's like the float on your commode is all it is. It's got a ball, a buoyant ball, and as the water level raises, it raises it and pulls it off the head and seat. Lets the water pass. As the water level falls, it lowers and closes off the head and seat. Very simple, very effective, a wonderful process trap. Inverted buckets, I like them, especially for dirty steam. They do a good job of handling water hammer. The weak link on these floating thermostatics is the thermostatic air vent. Spirax has a very robust one, and they can handle water hammer, but the weak link on these guys is water hammer. A couple other manufacturers kind of really make cheap little accordion style floating thermostatics, and they don't do well with water hammer. So back to, are you a Ford guy or Chevy guy? There's really no right answers on, hey, what's the best trap for a given application? There's some hard and fast rules, like if it's 10 PSI, 15 PSI steam, a drip trap, you're not going to use a TD trap. But what might make you use a F&T versus a bucket? Well, is there water hammer? Is that line hammering? Something you got to think about. If it's a hammering line, I'm probably going to stay away from the F&T. Although the Sarco, not that it's a sales pitch, it does a better job of handling it because it's just a lot more robust. One of the other manufacturers, they have the cheaper thermostatic air vents on the low pressure traps, because when we talk about an F&T trap and a bucket, that's dependent on pressure. In other words, if in F&Ts, they make them in 15-pound versions, 30-pound versions, 75-pound versions, 125-pound versions, 200-pound versions. You can use a 150 psi F&T trap on a 15 psi application. You cannot use a 15 psi trap on 150-pound steam. It will lock shut. So something else to keep in mind on the buckets and the buckets and the F&Ts, you got to match up the pressure to the line pressure. You know, the bigger the orifice, the lower the pressure. The higher the pressure, the smaller the orifice. So that's really what changes in those traps, is the size of the orifice. This balanced pressure, again, to me, it's an air vent. Don't see a lot of these. And this liquid expansion, that's a thermaton. So that's what you'd pipe up. Most traps, at least by a few manufacturers, you'll see a little 3/4 inch square head plug on the bottom of them, and that's for that guy to pipe right into it. So you're coming off of an air handler, you got a coil, you're draining into an F&T trap right here, and it's outside and you've frozen coils. That's a pretty good thing to put in there because it will dump. Preferably you like to see that dump somewhere, not just on the ground, because if it's outside, then obviously you're going to create a freeze, slip, trip hazard. But that's kind of a visual lay of the land of these traps. So into an F&T trap. So again, there's the float like on your commode. So there's the main head and seat on that trap. You can see that when the water levels up, it pulls that head off of the seat here. This is the thermostatic air vent. So on startup, on a warm-up load, the system's cold, this thermostatic air vent is going to be wide open. It's going to pass air as quick as it comes to it. So on startup, that's a huge deal. On process, that can be a huge deal. So on startup, this thermostatic air vent, wide open, passes all the air, passes the condensate, and then as it heats up, what it's doing, that thermostatic air vent closes right there. It's got a little alcohol water fill in there. As it expands, it closes that head and seat. Right there, it's showing. And now we're into just regular trap mode. And that float is just riding the load and letting it pass as quickly as it's formed. And F&T traps, as we say, will drain condensate under all conditions as rapidly as it's formed. So pretty basic stuff. All these traps, you can get them in NPT ends, you can get them in flanged ends, you can get them in all the different end connections. An F&T trap has to, again, if it's a 15 psi heat exchanger application, you'd get an FT. In the case of Spirax Sarco, it'd be an FT15. Or there's an FTI 15. What's the difference? An FTI is where it's inline. So that's an example of an FTI. Armstrong calls it something different. Watson McDaniel calls it something different. They all make similar traps. That's an inline FTI. If the came in one side and out the bottom, that's a parallel connected, and that's called an FT. They're both internally all the same. It's just, how do you want this thing to be piped up? Are you in a tight spot? Mechanically. Any questions on this one? Because to me, this is the star of the show. This, we've got animations for all these traps, but I want to make sure that this is clear on, why this thing's so much better than the traps that don't do a good job with air. It's all right there. So it's that thermostatic air vent. So something I didn't say, when you get in an extremely high condensate load situation, because condensate's not always like that, where it's a nice convenient little drip, drip, drip. When you get in a super high condensate load situation, this thermostatic air vent will actually open up, and it's like having two traps in one. So both of those will pass condensate. Much better than a bucket, much better than a TD, by far. You can rebuild these things. Generally, I sell Watson McDaniel. Generally, I sell Spyrex Sarco and Watson McDaniel. It doesn't mean we don't sell the other brands, we do. But with Spyrex, for sure, they sell, if you don't want to replace a whole trap and you just want to replace the internals, they have what's called a trap module repair kit. And that's where this bolt and this bolt comes off, the cover comes off, and basically the whole guts of this mechanism go in there. And it comes with a gasket for the cover. And that's actually if you buy all those parts separately, it will cost you more to rebuild that than it will if you go and buy the trap module repair kit, which is a lot cheaper. Now, at one point, these when people were saying, why would I pay almost the same amount of money for all the parts as I would a whole steam trap? That's when they came out with the trap module repair kit for people who like to repair stuff. But do you see anybody repairing traps at all? They just throw them away and put new ones in, right? Yeah, that's the world we're living in. It's like, man, there's no downtime anymore. Just route that stuff to drain and let's go. There's no time. So that is certainly the star of the show. F&T pressure classes, it's a bad picture, but there's that FT parallel connected, both connections coming in on one side. FTI, I just remember the I is inline, comes in one side, straight out the other. 15 PSI, 30 PSI, 75 PSI, 125, and 200. That's generally there is some FTBs and some higher pressure stuff, but that generally, you just need to know when you're putting in F&Ts, what the pressure is. But when we get into, and we'll talk a little bit about sizing, sitting really a sizing class, but when we get into sizing, you got to know, some process data in order to size it. It's not just hey, this is a 1/2 or 3/4 inch drip trap. Here's the old inverted bucket. This is normally open. So here's the main head and seat. So it kind of shows this for animation purposes slightly different than the way they're actually made, but it makes a good representation. So there's no thermostatic air vent. On this bucket, there's this little hole, and that's where the air vent is. And that's why it doesn't do a very good job. Some people have said a bucket trap doesn't know the difference between steam and air. And that's a problem on startup. When you're starting up a process, and what's heavier, steam or air? Air is 118 times heavier than steam. The first thing that's making it to the trap is air on startup. And for a trap that struggles to vent air or even decipher air from steam, what's going to happen when air hits that trap? That that bucket is going to become buoyant, and it's going to close off that head and seat. And all you're doing is backing condensate up, and your system's not going to heat up. So again, this is normally open. This is under cold condition here, and as live steam comes up, it will start to bleed the air through that little hole, live steam holding that guy up, keeping that head and seat closed, and then as soon as you make that phase conversion back to condensate, that's where that bucket falls, becomes non-buoyant, and lets all the condensate pass. Very simple density trap, good traps, do great with dirt. Again, the reason they do great with dirt is pretty obvious. The head and seat is right up there. Most of the dirt falls to the bottom. If you got a dirty system, a TD trap is not a real good choice. And we'll see that when we look at that TD, because it'll literally stop that disc from sealing off tightly. Any questions on this guy at all? Again, just like a F&T, got to size them for the pressure class. So it's not about that it's like a valve where it's a 300-pound valve or a 600-pound valve. It's more about the orifice. And if you try to use a 15-pound application, a 15-pound rated trap at 150 psi, it's going to lock shut. It's not going to work. The interesting thing about bucket traps is that they will lose their prime. So as you have modulating steam, there's a few conditions that can actually have you lose prime, but for, efficiency's sake of time, when you lose prime and your bucket falls and all you're doing is blowing live steam through, nothing is going to happen except blowing live steam through until you either A, go upstream and close a valve, or I like to go downstream and close a valve, and it will regain prime. As that fills up, that guy will eventually regain a prime. So if you're in a condition where there's a bucket trap at a plant or wherever you are, and you can hear like it sounds like it's blowing steam and it's a bucket trap, a lot of times what you want to do is go upstream, close that valve, and then slowly, give it a few minutes and then open that thing slowly up. And if that fixes it, we could spend 3 hours on troubleshooting traps and then talking about steam trap surveys. And you see a lot of steam trap surveys up here, the bigger steam users, pretty. Yeah. That's too bad. TD trap. So we've got this built-in little strainer. This is a cool trap. Not all TDs. This just happens to have one that's got an integral strainer. So this little disc right here, under cold conditions, is up. As soon as it sees live steam, the live steam actually pushes this disc down. So what makes this trap function is kind of like the same thing that makes an airplane fly. You've got to have a higher pressure on one side than the other. And it's basically, Bernoulli's theorem, whatever you want to call it. But we've got condensate in this case going through a strainer. And why it really makes sense to use the universal type strainer, that universal trap that has the strainer, is because you can see if there's a bunch of dirt or debris or pipe scale or any of that that's not getting strained. So that's the head, that's the main seating surface. What's going to happen? It's not going to close. And again, what's keeping that either up is when it's doesn't have live steam. As soon as it sees live steam, it's actually getting on top of that and holding that head down onto the seat. These traps are awesome, 30 psi and above, all the way up to 600 psi for the bar stock version. Great for tracing. My first choice for drip traps. This disc can be replaced, some people say a couple of times. This is an induction hardened seat surface that's very hard, and you can it's just got a little screw cap, and I'm sorry I didn't bring you guys cutouts. I know you asked for cutouts, cutaways. I don't have those. I will have some of those very soon. But this insulated cap just threads off, and you could put a new disc. I say one time, and then you throw the whole thing away. In the case of, we'll get into some trap stations and universally connected traps where you can just take 2 bolts out, chuck off the trap, and put a new one on. And in most cases, those have isolation valves built right into them. And that's a really good way to go, especially when people don't have a lot of time or you can't take process down. So that's a TD trap. Not going to spend a lot of time on the thermostatic trap. Again, I see these as air vents. I just got into a spec thing on a bid spec job for a pharmaceutical where they needed a 300 psi air vent, and it said a certain manufacturer right in the specs and said that they needed to be stainless and rated for 300 psi. Well, that's what we spec'd in because that is an air vent. But the engineering firm kicked it back and said, you gave me a steam trap, not an air vent. And I said, well, go take a look in the verbiage where it refers to it as an air vent, and the manufacturer that you've chosen as your basis of design, their air vent's only rated for 250 psi, and the body materials are cast iron. So if you want what you put in your specs, that's what we're going to use. And it's been like 2 days and I haven't heard back. So, that's how that goes. Anyways, long story short, we got an alcohol water fill in this that when it gets heated up, that's the head and seat. It expands. So on startup, this thing is wide open. Passes air like nobody's business. Great air vents. Passes condensate. When it heats up, that alcohol water fill expands and closes off that head and seat. Don't see a lot of them. Pharmaceuticals, see them more as air vents than anything. Pharmaceuticals, food plants, and some sterilizers. How are we doing on time?
What are you saying that they vent to? Are they venting to the atmosphere or back to the DA tank?
Yeah, usually back to the, yeah.
I don't know what time it is.
You'll have to keep me honest on time. It's 7:13. So what time are we supposed to be done? Okay, perfect. That'll be good. Again, we talk about, are you a Ford guy, are you a Chevy guy? It's really not one always right answer. This is kind of right out of a Spyrex Sarco steam trap selection guide. This is steam mains. They're saying our first choice, floating thermostatic. They're saying really that's it. That second choice, so that's though 230 psig. That's not my first choice. I don't like that trap and that application. That trap, that is my first. That is my. I'm sorry. They're saying the floating thermostatic 0 to 30, right? So that is an agreement 100% with what I believe. 30 to 400 psi, a TD trap, 0 to 600. They got the TD all the way down here until they get into a separator. And again, the reason you're usually seeing the F&Ts, and I think it's the right trap for the application, is because as a heavy load of condensate comes through, that thing will drain it just as quick as it comes. And should it be greater than what that float will do, the thermostatic air vent will open up, and then it's like, 2 traps in one. So first choice on a moisture separator, F&T. Steam tracers, you see the TD, balanced pressure can work. I don't want to back up a lot though if it's outside. I don't want to subcool because remember that was a subcooling trap. Heating equipment all day long, man. Shell and tube, heating coils, unit heaters, plate and frame heat exchangers, all day long. It's the F&T. Notice that this balanced pressure on the radiators. That's basically a radiator trap. That's really where, and nobody really hardly has those anymore, and why we're not seeing a lot of them. General process equipment. This is really where you get into, it's still F&Ts. Steam mains, same thing. So Inverted bucket. Notice inverted bucket gets some good checks. So this is an important one. So drip legs, dirt legs. A lot of times, I just told you that, hey, a drip trap, it's a 1/2 inch or 3/4. They do make a 1-inch TD trap. There's probably not an application in North America for it, despite the fact that we sell them a lot. And we tell people, hey, that's really oversized. In these steam mains, there's really not that much going on. You might need a trap that's going to pass 200, maybe 300 pounds per hour, which the TD traps are well over, the capacity is more than good for that. But I told you, you need a 1/2 inch or a 3/4 inch trap. So you got a 6-inch steam main, and then you bought a 3/4 inch trap, and you took the 3/4 inch drop and a 3/4 inch pipe. What's going to happen then in this scenario? It's not going to drain very well, is what's going to happen. So we call it a full-size drip pocket. So in this case, what's going to happen is this is going to back up with water because the velocity is going to be greater than it'll allow it to fall. We've got to encourage that condensate to fall in the drip leg. And what's actually going to happen is this is going to back up water. It's going to kind of create a venturi and throw water down the line. That's what's going to happen here. So the way that should look is like that. That's a proper sized drip pocket. And we say full size up to 6, and then you can go half over that. It shouldn't be smaller than 6 though. So if you're in an 8-inch line, I'd still use a 6-inch. When you get into 12-inch lines, that's where you're really using a half size. So full size, no smaller than 6. So if you got a 14-inch steam main, a 6 will do fine. An 8-inch would do fine. But we want to encourage that to fall in. We like this measurement right here, about 18 inches. And then we want to come up about, 4, 5, 6 inches. That gives a spot for dirt and debris to collect here. If you're really slick, you're going to stick a ball valve here so that you can blow that dirt leg down, hopefully once a year. Again, a good piping practice is strainer before that trap and then a check valve right after that. That makes sense? We're going to encourage that flow. So that's kind of just showing a same exact thing in a different way. This scenario, it's just going to pass right over, and then whatever backs up, it's just going to get thrown down the line. So that's a pretty good looking steam main right there. That's got our hydraulic head, and we've got a spot that comes up and gives it a place to collect. And the only thing I'd like to see more is just a little ball valve right there. Drip trap sizing is simple, 1/2 and 3/4. Yeah, there's a few exceptions. Not many. Popper process trap sizing. Some considerations. What are you trapping? What's the equipment? What's the steam pressure? Is it saturated? Is it superheat? Again, superheat doesn't really have any moisture in it at all. I like TD traps a lot for superheat. Is it constant or modulating service? What's the back pressure? What's the capacity? So again, we said it earlier, when you're looking at tags and you see 1 million BTUs, just really drop the last 3 digits and it's going to give you 1,000 pounds per hour. It's not perfect, but it's close enough. It's in the upper 90th percentile. And then, the challenge is going out in the field, trying to troubleshoot problems. Nobody has gauges. Nobody knows what their flow rates are. They don't know what the pressures are. There's so much that they don't know, and it's not their fault. It's just a problem. They work in a plant and they've inherited this, and their specialty is focusing on this, and they need somebody who knows steam to come in and help them. It makes it very hard to help them when we don't know stuff. So, just a handy little 40 GPM. GPM divided by 2 times 1.1 times 100 will give you pounds per hour. Pretty standard stuff. Process trap sizing. So, in the case of the unit heater, you need to know the unit BTU rating. On a shell and tube, you want to know how many GPMs of water being heated and the temperature rise and what pressure steam you're using to heat that. We could do a whole class on sizing traps. Didn't really intend to do that today. Steam coils, CFM airflow, physical size of coil, temp rise of the air using what steam pressure. It's basically the same. That's how we're sizing process traps. It's not hard, but you definitely want to do it right. There's safety factors. Or give a, kind of a rule of thumb here is below 30 PSI, size at a half PSI differential of full load. And when we get above 30 PSI in process applications, we're sizing 2 times the load at full pressure differential. This is a double block and bleed. So this is a steam trap station. And you can see right there, instead of having the gate valve, so, gate valves, that's an isolation valve. Globe valve's meant for modulating. We see people do some crazy things with valves. Isolation valves should be gates or balls. We don't love ball valves just in the way that when you're opening steam valves, you want to do it slow. It's why they're usually multi-turn. Ball valves are great. They seal off wonderfully. They don't have packing like gate valves, but people like to open them up and close them really quick. And so this is just really meant to show you, this is a typical steam setup. We've got the gate valve, isolation valve. We've got the strainer. That's the Spirotech, loss detector. There's your trap. There's a check valve. There's that. You can put all that right in one small package. And again, when you're working in systems that you can't shut down, you got the isolation valves right there, 2 bolts, that trap comes off, bam, slap the other trap on it. So they just recently come out with these where they're flanged. So for heavier, higher pressure and greater capacity. So that's a brand new product. It's pretty good and all stainless. They used to, they still only go to 1 inch, but they're 150, 300, and 600 pound class with the raised face flanges. This is like if you're working at Nestle, their spec is even on a pressure gauge, double block and bleed, which is a little overkill, at least the plan I call on. But we've got double block and bleed, and then there's the trap. That's a new product out that's really slick. There's an increased capacity trap, so greater capacity. It's got an inline.
Can you go back to that?
Yeah, of course.
The difference between 304 and 316 as far as which is better? Or?
Well, 316 is more corrosion. We all know that stainless isn't as strong as carbon. Carbon is stronger than stainless. But when we're talking the erosion corrosion of steam and condensate, I'll take 316 all day. I don't see many people footing the bill from a piping perspective. Blank sheet of paper, if I'm designing a steam system and somebody's trying to be tight on, their finances, put Sketch 40 on the distribution and Sketch 80 on the condensate return. The condensate is worse usually. If everything's sized right, you don't have increased velocities. I'd rather see personally myself seamless on everything, 80, all across the board. But as far as to answer your question, 316 stainless L, low nickel. Oh yeah, absolutely. But most of these traps that have gone, and again, it doesn't matter what manufacturer, and I lead with Spyrex, but it doesn't mean that Armstrong and everybody else is not making good equipment. They all make good equipment.
Guys that work for Fire, we're not going to do anything if we can't double block it on a live steam system.
Is that how you guys do it?
That's it. Going to have two valve.
That's brand new.
That's like
It is really slick. I was impressed by it.
So you understand what that means, right? Everybody?
Does that mean if I go to sell a trap, I have to double block it, is what
What,
you're
what I'm saying is someplace like the spring, we're not gonna isolate with one valve on each side. When we're running at 70 pounds or 30 pounds or whatever. We're gonna shut the plant down. To work on anything.
saying? Okay, so you're saying we're not gonna,
Well, yeah, wouldn't hurt my feelings to sell these, but what I'm getting at is the stuff that's existing, we're gonna have more than one valve to isolate on both sides.
For safety.
Do it on Christmas Day, yeah.
how would you have multiple valves on both sides, on the discharge side, on the condensate side? You're saying somewhere downstream there needs to be at least two valves?
It's built-in, safety, is what it is.
I understand what it is, but you're telling me that there's gonna be multiple valves on the condensate discharge side, the downstream side?
So no, if there's not,
To
we're
the
not,
process.
if there's not, we're not gonna do it live. That's what I'm saying.
The system needs to be shut down.
There's no.
Well, because look, there's a lot of live steam and condensate, you know,
It only takes one.
especially those who, and maybe we should have, maybe I should have done less on some of the other stuff and more on the trap testing and troubleshooting in the field, but
It's just that you brought this up and it was a point I wanted to make.
that is slick as snot, and it's why it just came out, and it's why I put it in there. And Nestle, I had problems specifically finding the right valves to meet their spec, to be double block, to be true double block and bleed. And when I saw that just like 2 months ago when I went to the factory, I was pretty impressed by that. Yeah.
Does our ammonia refrigeration have anything to do with the atmosphere that these are exposed to?
You guys could tell me a lot better than I could on that.
Probably does.
Probably, yeah. I mean, my refrigerator is probably jacking up my ozone sitting right next to my desk at home, you know.
I don't think the ammonia process is gonna have anything to do with that, because the ammonia process is all contained, 100%.
Well, usually.
I mean, that's the purpose.
Yeah.
You don't.
Hopefully,
have any
right?
leakage, so ambient ammonia is not gonna affect this, that's not why it's stainless. It's a food manufacturing process.
Well, it's that. Well, and yeah, specifically, look right there. I mean, they're saying healthcare and food and beverage is the sweet spot for this. But I'm saying anytime. Now, we don't want to do dissimilar metals, but on condensate return, anytime we can use stainless, it's advantageous for sure for the life.
Sorry for the interruption.
No, I appreciate it. That's what I hope for that. I mean,
Well, I'm hoping to find a customer that would pay for a stainless condensate line. I haven't found too many that would pay.
me either. Me either.
I mean, I'll come help you out.
Well,
I'd go into sales.
I do.
They're in a big market for that in Ohio, especially on the east side.
Fair. I will.
Be real about it. I mean, it's awesome. because
Well,
we can talk to people about this and offer this service, but
Yeah.
in reality,
people are though installing these on black iron lines. I mean, you know, there's a gasket separating, and in the case of that guy right there,
Well, to me,
All
this
day
is a
long.
Safety device right here.
Yeah, it is. Yep.
Double block.
But I'm with you. If people were buying stainless, you know, lines for their condensate all the time, I wouldn't be a steam specialist.
they don't even
I'd be a
have
general
sprinkler
line
lines, so
salesman.
don't worry about the stain.
I'm with you, brother. So again, this is just 304 body and cover, but this is a
Spear cake once, so
yeah.
honestly, return cake, so it can't happen.
This is a neat new trap that, again, you can't see it very well, but there's a bolt here, there's a bolt here, and it doesn't have the built-in isolation valves, but this is just a universal pipe connector, and then these two bolts, you obviously got to shut steam or isolate upstream with gate valves or ball valves or something, and then two bolts, that pops off, you pop a new one on. These cannot be rebuilt, those are throwaways. And that's the real world.
Our double block right there, babe.
And that's the real world. So
Startup venting.
this was kind of the sheet, which we're not going to really go through it too much, but this is good information. These are all, it's kind of like going to the doctor and that form that you fill out. Are you having this? Are you having that? Because these are all telltale signs of very common conditions.
Turn your head and cough.
Turn your head and cough. So that's I haven't been asked to do that in a long time, and it's good with me. Yeah, it's good with me. Anyways, that, I gave every one of you guys a sheet. There's more up there. Those are handy. I mean, you look into it and you go, oh, I see that every day. Yeah, I see that. I see that every day. So that water hammer's next. We're not going to get into it, but for sure, when live steam traps are blowing through, what's going to happen is live steam is going to get into the condensate return lines, and it is going to create differential shock. And the lab that I'm building, Macomb in Columbus, I came from a place where I had a lab and we taught classes with real equipment where we can show you all the stuff in real form. And I'll have a water hammer display there, which will kind of be a mock-up. It won't be actual live steam and the condensate return, but it'll be glass piping with green antifreeze and a black light over it with air hitting it. And what it's doing is basically just, it's creating wakes in the ID of that pipe. And once the full ID of that pipe gets filled with condensate, that's where it hits. And you guys have all heard it in plants, and damage can be done. And, the truth is it's kind of fun mocking that little deal up. But when you get into, the big world, what are we calling this? Flange by butt weld? I mean,
I'm gonna send you a video of a guy getting blown out of a manhole cover.
I know exactly which video, and there's no joke about that. And that's serious business. So
He got his head out of there. Right.
Yep. Was that at Detroit Edison?
I think it was in Boston.
Oh yeah, okay, that's right. So, any questions? Hopefully it's been useful.
The rest of the pipe, it's not in the picture?
It's
It's in the building.
yeah, it's probably somewhere. Yeah, we're calling this flange by butt weld, but yeah, that clearly had a flange on it. That's an old picture, but there's certainly modern versions of it.
Man, we'd like to thank you for
Oh, you're welcome.
presentation time.
Awesome.
Thank you. Hope to have you back too.
Thank you, man. Appreciate it. Yeah, I mean, if you guys ever, look, I try to make it as pointed and as to what you want to talk about. But if you want to get into sizing traps, or you guys want to talk PRV stations or control valves, condensate pumps, whatever it is that, you want to talk about, I threw this together. I probably should have spent about 4 hours on it. I threw it together in about 2 hours today. So,
Well, if you spent 4 hours, we'd be here till midnight.
well, no, it would have just been a better presentation. That's all.
Thank you.
Thank you guys. Appreciate you having us in.